Fancy meet computers. How is everybody on this totally jammin' Friday afternoon? This is your DJ for the afternoon, DJ Kickin' at DCRF3MF-FM, your modern place for all your classic hits. Everybody's still dead? Is that the thing? Everybody's still dead? Probably everybody's still dead. Quoi? Every once in a while I like to do this shtick where I'm like a radio announcer. It's like, you know. It's like, welcome back to WKR3FM, your smooth jazz radio station. Your favorite for all your smooth jazz favorites. WKR4! You know, I don't know. I like radio culture. What can I say? Let's see. I think we talked about garbage collection, right? We were on to storage, I believe. Yeah, I remember saying that line. How far did we get into storage? I don't think we did this stuff. Yeah, I think this is where we are. Yep. So, should we wait for the rest of the class to show up, or should we just go for it, guys? Yeah? I think we should just go for it. We got, you know, we got a lot of lecture ahead of us. I don't think we'll be able to cover it all this week. Especially at the rate he goes, someone in the chat says. So we've been talking about memory. We've been talking about how to model memory from like a top, we're kind of going top down with this particular lecture. We're sort of starting with the effects of memory and like what we can do with it. And now we're going to work towards formalizing these rules. So we're going to talk about what storage actually means. How do we model memory storage under our current organization? Like, everything we've done so far has been fundamentally modeled in set theory, right? So the question really is, how do you model computer memory as set theory? Because, you know, set theory is the most general mathematics set that we have at the moment. So pretty much anything can be modeled with set theory. Anything that exists mathematically, at least. And certainly computer memory exists mathematically. So let's get to it, shall we? One question that should naturally occur to us, now that we have expanded our set of types to include references, is what does a reference value look like? So far, we have been renaming such values as variables without really exploring the concept. In our previous example programs, we have been using our intuitions about how a computer memory system works to fill in the gaps of how memory is stored and retrieved, right? we've been basically, throughout all of these examples, we've been using our mental model for how computer variables typically work to try to fill, to kind of stucco between the gaps that we haven't filled in yet. So let's fill in the gaps somewhat. So, in order to accurately model memory in our mathematical environment, let's examine how memory works in very general terms in a computer environment, right? Most of you will already know all of this, but hopefully, anyway. In most computer languages, memory is modeled as an array of bytes. The runtime system keeps track of what bytes are currently in use, and by what. When more memory is requested, the size of the requested memory is passed to the runtime system. A free region, large enough for the data being allocated, is found or not found, and then the runtime system marks that region as being used and returns the index of the newly allocated region. So if you... 1MD3 asked so many good questions in tutorial today, it caught me off guard. Wow! Good questions are good, though. That's awesome. Maybe they're learning! Impossible! First year's learning? Good lord. Anyway, so the way that memory works in general, roughly speaking, is precisely the same way that you use dynamic memory allocation in C. You know, the something like a malloc operation is implicit during variable declaration, right? Essentially, some subroutine of the program goes and looks at the table that's being kept of existing memory locations, within the allocated memory for the program, finds a location that's blank, and returns to that to the program that requires the allocation the address that it's giving it, and then it updates the table to include this new address being allocated, right? It really is useful to think of like a table of declared memory addresses as being a secondary sort of organizational structure that's being used by the program. So, for our purposes, such messy implementation details are unnecessary. The first thing that we don't need to worry about is how the values are being stored. So we don't need to know that all of this data is being stored in RAM, or if it's being stored in register memory. We don't need to know if it's being stored on the hard disk even. We don't need to know the physical memory apparatus. All we need from that as an abstraction is that you can put stuff in it and get it back out later and it'll be the same thing still. Like, all we need is a reliable storage and retrieval mechanism. Yes. So, as opposed to thinking of computer memory as an array of bytes, we can think of it as a memory store. We can think of it as a group of values, a set of values, if you will. So basically what we're abstracting at the same time is we don't necessarily, for the purposes of these mathematical calculations of ours, we don't need to worry about memory addresses per se, right? A memory address in your RAM, like a pointer value, is like, we don't need that level of information about it. We also don't need to know that references themselves are numbers. So, let us take memory references to be elephants. Um, let's take memory elements, not memory elephants. Good lord. He's dead, Jim. I'm sorry. I did. My brain was broken. Yeah. Garam. Good lord. Okay. Okay. So, let us take memory references to be elements of some uninterpreted set L of store locations. So, memory for us is going to be a set, right? So L will be a metavariable ranging over the big L. So the big L is all of our memory locations. Little l is some particular memory location. Any of them, but just one of them. We will add L to the terms of our language to mean a memory location value. The memory store itself can then be simply a partial function from locations, L element of the set of locations, to our set of values, V. So because this is an uninterpreted set, you could easily think of this, you could easily populate it in your brain with, like, numbers, right? It's like, oh, I've got location 1, 2, 3, 4, 5, 6, 7, etc. And that's a fine way of going about it. You know, if you need a more concrete model than this in your mind, just use natural numbers as, like, actual physical address locations. That's fine for a mental model. But what we need is a more abstract version that gets away from those messy implementation details. There are actually problems with thinking of memory locations as numbers, as we're going to see. So, the memory store itself can then be simply a partial function from locations in our set of memory locations to our set of values, V. So, in the same way that our typing relation maps from terms to types, our memory store is a mapping from memory locations to values, right? So that's a very, I'll say it again. The memory store itself is a relation mapping locations to values. So, we will use the metavariable mu, or mu. I don't know, do you guys prefer mu or mu? I'm going to say mu. The puns I have coming up will only work if it's mu, so. We will use the metavariable mu to range over the set of possible memory stores. In our equations, we will use mu to mean some arrangement of memory. So, we now have mu works with the zoo. That's true. Ha! I'm a poet, and I didn't even know it. So we now have a metavariable mu. Or mu, whichever. It's going to function very, very similarly to gamma, actually. So, all of the stuff that you learned about how we organize gamma is going to be roughly applicable to mu, sort of from top-level details. That is to say, it's going to be a set... yet you still showed it. Yeah. So it goes. So we're going to carry... Basically, in the same way that we carry gamma through all of our evaluation relations or typing relations and all of that kind of stuff, we are now going to have to also carry mu through all of these things as well, because it's going to represent whatever the arrangement of memory is that we have at that time. If we have a metavariable about it, we can perform transformations over the metavariable that describe changes in the state of the memory. Ta-ra! Which is what we want to do. So, From now on, we will refer to references as locations, and the memory storage device simply as the store. So this is to emphasize that we are now talking about set theory. We're going to now use this nomenclature. So, getting seasick. By modeling our memory this way, we are intentionally distancing ourselves from the way that memory is managed by C and related programming languages. Because we are not interpreting our locations as numbers, we do not have to worry about what happens if we try to perform arithmetic over them. That becomes the natural question. It's like, well, if this is a number, what happens if I add them together? What happens if I subtract them? It turns out that pointer arithmetic is notoriously problematic when it comes to type systems. So any well-typed language, like basically the more well-typed your language is, the less likely it's going to give you direct access to pointer arithmetic as an operation that you can perform as the user. So let's say, for example, some location in memory is of type float, right? You put a float in there. This tells us absolutely nothing about what might be stored at location n plus 4, right? It's like, even if location n plus 4 is being used by some other part of the program, because you're accessing it out of context, any typing information for that location has been lost through the pointer arithmetic operation. So generally speaking, pointer arithmetic not considered type safe. And again, the whole point of this entire damn course is to try to encapsulate all correct behavior inside of a type system. So, if it's not type safe and it can't be made type safe, we think, well, it must not be safe in general. So we try to exclude that from our language if possible. So, how would we go about typing an operation like this without actually executing the program? It would be impossible, right? For one thing, in C, unless it's declared as, unless these are components in an array, you can't assume that location n plus 4 is even being used. And if it is being used, you can't assume anything about which variable is using it, right? It's essentially random. So that's why we're not using numbers. I'm going to ask if this all makes sense. Does this all make sense? I kind of like the direction that the course has taken in this last month, because we're finally actually talking about how real programming languages are put together, you know? So, good. So, the mysterious 151st Pokemon. We can conceive of the context provided by mu similarly to how we already talk about the typing context gamma, right? So that's one thing, like that's something you could think of mu doing, is providing context, right? Rather than being attached to the typing relation, mu will instead attach itself to terms, right? Mu has evaluation significance rather than typing significance. So it attaches itself to terms and not types like gamma did. It's kind of like, you can think of it as like a gamma but for terms a little bit. So, when considering the evaluation of t, some term t, it is possible that evaluation will have a side effect on mu. We therefore modify the general form of the evaluation t evaluates to t prime by adding two different state contexts. So, t evaluates to t prime gets changed to t with context mu gets evaluated to t prime with context mu prime. Now, This is why std : list sucks. It forces pointer arithmetic to traverse the list. Yeah, right? My point exactly. So the thing about this, right? In 99% of cases, mu is not going to be modified, right? For most of our evaluation inference rules, there's no side effect. So mu and mu prime are going to be the same. However, because the possibility exists, we have to acknowledge that the possibility of changing mu exists. That's why we have mu and mu prime. But, proving that mu equals mu prime is essentially the same as proving that an evaluation has no side effects. Oh, why is it backward? It was gamma before the turnstile, now it's mu after the t. I don't know. That's what the textbook does. Buggered if I know. So, as I stated, if no side effects happened, then mu is equal to mu prime. Otherwise, the difference between mu and mu prime represents the effect on the state of the evaluation of the term t. In effect, we have enriched our notion of abstract machines so that a machine state is not just a program counter, represented as a term, but a program counter plus the current contents of the store. So, there you go. Is that because most languages declare type after variable name? Well, mu doesn't really have anything to do with type. For gamma. Yeah, probably. It's like, I'd say there's a bit of a semantic difference as well. Like, when you're talking about typing, you definitely, you're more thinking about, I prove this type from the typing context gamma. Whereas with mu, you're not, proving the value of a term using the context mu. It's more like you interact with mu as necessary in order to evaluate the term. It's like, I guess what it is it's placing mu conceptually in the category of a result rather than as a precondition. But, and a secondary result, that's why it comes second. That's my justification. There you go. So, let's refactor our evaluation rules for pure lambda calculus in light of our new rules. So, the following, these should all be, quite straightforward. If we have application for a lambda abstraction, right? It's like the application term and mu evaluates to the substitution and mu. Note that these two mu's are the same. Pardon me. For EAP1, T1, T2, and mu evaluates to T1 prime and T2 and mu prime. This is because this is dependent on the evaluation of T1. The evaluation of T1 may have side effects, so we have to update mu as well. And the same thing for EAP2. So the interesting thing going on here is the EAP abs, it's built into the semantics of the language, function application has no side effects. Right? That is what that's saying right there. Function application has no side effects. Mu remains constant through function application and the subsequent substitution. If you think contextually, gamma is the context prior to the function after the turnstile, but mu is the coexister that mutates along with var t. Yeah, exactly. Yeah, precisely. Have you guys been appreciating how terrible these puns are? I hope you've been appreciating how terrible the puns are. So, let's examine some of the subtleties here. Note in the two congruence rules, EAP1 and EAP2, we presume mu may be affected by the evaluation of T1 and T2. Whether or not this is true, the change is reflected in the overall evaluation. However, with EAP-ABS, we have the same mu as before and after. This is one way of stating that the function application has no side effects. The only operations we have so far which affect state are allocation and assignment. Since there is no sub-evaluation implied, we know that mu will remain unchanged. This property will be useful later on. So, essentially, the problem with EAP1 and EAP2 is that we don't know whether or not T1 or T2 contain either an allocation or an assignment operation. If they do, then mu is going to change, and that change needs to be reflected, right? Whereas with application, we don't really care. We're not actually evaluating T12 here, right? We're just performing a substitution over it. So because it's not being evaluated, even if it is an allocation operation, we don't care because we're going to evaluate it later, not during the function application itself. So here are the terms. Formally, we will add the following terms to our calculus. So, in terms of terms, so to speak, the terms that we're adding are reference t, dereference t, so allocate t, dereference t, assignment of a term to a term, and a location L. So here's an interesting thing, right? You would think that this t might be, like, correctly described as a location L. But in fact, what our calculus allows for is it allows for the location being assigned to be calculated. So that's kind of interesting. So basically what that allows us to do is it allows us to store locations as values in the memory store, right? So we can perform a dereferencing of one location to obtain another location and then assign to that location. So in that way, we enable the same types of pointer arithmetic that you can, or not arithmetic, but like pointers to pointers. That's what this allows us to do, is pointers to pointers. Locations to locate, or locations having locations as the values that they are pointing to. Haha! Further, our complete list of values becomes lambda abstractions, the unit value, and locations L. So the reason that locations are values is because you want certain operations to stop when they hit one, right? A location, like a reference evaluates to a location, like an allocation operation evaluates to a location. Once you have a location, that should be sufficient, right? But, So, while we have added L to our calculus, we do not necessarily intend the programmer to ever directly use it. We intend L to encode intermediate implicit results of calculations rather than explicit ones. In other words, we are working on the internal language. L is available for constructing derived forms, but our goal is that the locations can be safely ignored by the programmer, unlike in C programming. So most programming languages attempt to hide actual memory locations from you, the user. Man, I'm just batting 1,000 today, aren't I? Good lord. So like, if you think in, like, in Python, like, you can expose the memory locations of your data structures if you want to. But through regular Python use, you don't have to think about it. You don't have to worry about how things are being stored in memory. this is one of the implementation details that we're trying to take off of the programmer's plate, right? It's still, because I teach a C course, I always say to my students, it's still valuable for you to know how the memory mechanisms work. That's what that's one of the huge benefits of learning how to program C is you understand how the computer works. And it's always going to be useful to understand how the computer works. But in terms of like the day-to-day business of programming, it's not necessarily useful to have to mess around with memory locations all the time because it's prone to error, right? So let's talk about the evaluation rules for our memory operations in somewhat more detail. Now, taking into account the fact that we have the memory store mu explicit in our calculus. So, let's formalize our evaluation rules first for dereferencing. So for a dereference, we have a congruence rule, which exists as all congruence rules do. And then we have the dereference location rule. So if we are dereferencing a location, and we have as a precondition that this is like, since we're considering mu to be a function, this is like function, like mathematical function application notation. So this is like you apply L to mu and you get the corresponding value out. So assuming that when you apply L to mu you get V, then dereferencing L yields V, and the context remains unchanged. So this is actually a problem sometimes that this is a conceptual problem people occasionally have with dereferencing operations, like particularly with pointers. Sometimes people think dereferencing is a destructive process, but in fact it isn't. Mu is unaffected by dereferencing, so nothing is added to it, nothing is taken away. You can read as many times from memory as you like without modifying the memory. Yeah. I like a native function that cannot be represented by... like a native function that cannot be represented by lambda functions. Yeah, it's like... It's like a function application that exists inside of the set theoretic, like... How to put it? We've built everything so far out of set theory, right? This is an element of set theory, not an element of the language, right? But yeah, it's like... If you have a relation from terms to values, or from terms to types, for example, and you apply a particular term, you get a particular type. That's kind of what it's saying, but anyway. We should all know what function application is. So, the congruence rule, deref, lets us evaluate T1 until a value has been reached. Then, if a location is the result of evaluating T1, and if L is an element of the domain of mu, we can replace dereferenced L with the retrieved value. Note that dereferencing anything other than L is disallowed by the set of evaluation rules available. So, yeah, in order for this to actually work, you need a location, but that shouldn't come as a surprise. That's the whole point of the type system. So, having a relation, we are comp size. That's illegal. Ha! Linux is the brotherhood of datelessness. So we've talked about dereferencing. Let's talk about assignment semantics. So we've got two congruence rules here. This should be a very familiar form because this is essentially the same form that application takes. It's actually quite similar to application. application semantics. You've got two congruence rules. The first one evaluates the first term. The second one evaluates the second term, but only in cases where the first term can't be evaluated. And then you have the actual application. So if the first term evaluates to a location and the second term evaluates to a value, then what is produced is a unit, like the unit value, with a mapping of L to v2 in mu. So this is an important distinction, right? So we're using the maps to arrow a little bit differently than we do under lambda substitution. It's like, I'm going to update where this particular location points to, right? Which is different from the substitution that we've been doing so far. So, once again, we are required to fully evaluate T1 and T2 via congruence rules before performing the assignment. The assignment itself requires a location and a value. The notation L maps to v2 in mu means a store which maps L to v, v2, with all other locations, mapping to the same things as in mu. So, one important distinction. Unlike with Python dictionaries, you can't produce a new location this way. Like, if you, for example, if you evaluated this to some L that had not been used yet, this doesn't work. I prefer the syntax for adding a relation to gamma. Yeah, well, the point I'm trying to make is that we're not adding a relation to mu in this case. We're remapping one of them, right? We only add locations to mu through allocation. We can't add a location through assignment, right? Yeah. So, this is allocation. Again, we've got a congruence rule, but the interesting one is, so if we have ref evaluating to some if ref gets a value, that evaluates to some location with mu equal to mu concatenated with a new mapping from L to the new value, right? And the precondition for this is that L is not in the existing domain of mu, right? So essentially, we have to pick a fresh L. We have to pick a fresh location and create a new mapping in mu between L and the given value. So, to evaluate allocation, we must first evaluate T1 to a value using the congruence rule eref. Then we select a fresh location L not already used in mu. We extend mu with the mapping between this fresh location and the given value. The term itself directly evaluates to this fresh location. That will be buying memory bars instead. Yes. Yeah, it's like allocation is buying new memory. Assignment is just remapping old memory. So, any questions about that? Any questions? So is the, do you have any questions, poll mostly an awakeness test? Okay. Well, if you have any questions, ask them. Oh, sorry, could we go over the rules once more quickly? It's a mouse sensitivity challenge. Yeah, okay. So, very quickly, dereferenced. In order to dereference a location, you need the term to evaluate to a location. You need to look up the location in mu, find the corresponding value, and replace dereference L with the value. With assignment, if you are assigning a value to a location, that evaluates to a unit value, which is to say a void type, and then whatever L was originally mapped to inside of mu, you change that so that it's now mapping to v2. And with allocation, if you have a reference, if you're trying to create a reference with value v1, you look up a fresh location in mu, right? And you this guy will evaluate to that fresh location, and you extend mu with a mapping from that new location to the value given. So, let's talk typing. Now that we have formalized storage and retrieval of values from storage, one question remains. What about the typing? We will answer this question by elaborating on some of our natural intuitions. So, we could start, like our first pass approximation of how you might go about typing a location. We could start by saying that the type of a location in storage should be the type of the value stored there. This would yield a typing rule such as the following. So, if L would be typed reference to T1 in the event that mu at L has type T1, right? That is, to type a location, we look up the value at that location and type it, right? Bing, bang, boom. Pretty simple solution. Here's the problem. Well, yeah, here's the problem. So, in effect, by making the type of a location dependent on the program state, we have changed the typing relation from a three-place relation from a typing context gamma and a term t to a type t. We have changed that to a four-place relation from a typing context gamma, a memory state mu, and a term t into a type t. So essentially, you have to add mu to the prerequisites to the typing relation, right? Because that's now required. All the rest of our typing rules will need similar modification to this. So basically, we just drop mu in here beside gamma, right? Most won't do anything interesting but with mu, but most will need to pass mu to subderivations. So anytime you have like if it's a value, then who cares? But if there's a subderivation involved, you need to be able to pass the mu through, right? So, this approach has two big downsides, however. First, we have made typing a term dependent on typing another term. If we have something like the following situation, where terms stored in memory are dependent on other terms stored in memory, things get quite hairy very quickly. So consider a mu that looks like this. So L1 maps to lambda x 999 with x typed natural. Location 2 maps to lambda x dereference L1, essentially. L3 is dereference L2, L4 is dereference L3. You can imagine a whole string of these. It's a contrived situation, but believe it or not, this type of thing can actually happen. Not only would we potentially have to evaluate a lot of locations to get to the type of any one particular location, we would also have to recalculate it each time. So this is, although it's simple from a conceptual standpoint, it's complicated once you start, taking into account the complexities of the situation. like, in general, you should not have your typing relation dependent on evaluation semantics at all, right? So this is not even as bad as things can get. What about the following? So if L1 requires the dereferencing of L2 and L2 requires the dereferencing of L1, congratulations, you just caught your type checker in an infinite loop, my friend. And it turns out that such structures do actually exist in practice. Doubly linked lists are an example. So any self-referential data structure is going to immediately break your type checker if you require, if you have to go into the memory and type check the values there in order to type any term, right? So, surely we can make this more efficient. Let's recall the following information. Number 1. The type of a location is derivable upon allocation of the type of the instantiating value. So, according to our semantics, we are only allowed to assign values to locations of a matching type. The thing we are constantly recalculating has been fixed from the start. So, when we perform an allocation operation, if the allocation operation is well typed, which it should be, we can derive the typing of the store from that. So we don't need to recalculate it if we keep track of it. So, rather than relying on our memory store, mu, let's create a new typing store. So, we're actually carrying two different distinct types of memory here. We have mu, which maps us into values from a particular location, and we're going to have sigma, which maps us into types from a particular location. So, we are expanding the definition of allocation so that when a new location is allocated, a corresponding entry in sigma is created. Just as mu is a partial function from locations to values, sigma is a partial function from locations to types. So because we now have a sigma, which allows us to pull out the types of any location that we may desire in one step, we neatly sidestep all of these problems with, typings require the typings of other things, which require the typings of other things, which possibly gets into infinite loops. Any questions about that? Cuestiones. I can hear some shaking sound whenever you touch the desk. It seems that your camera isn't fixed tightly. Hopefully. Yeah, it was the top of my laptop bumping against it. Yeah, I need to actually do a proper bracket for this damn thing. Sacrifice storage space for efficiency. Love it. I know, right? It's almost like this is like the type of thing computer scientists do routinely, you know? And it's not just efficiency, right? We are now making possible things that were previously impossible, like typing circular references. And one other thing to, we know that it must be of a particular type in order to create it, but it's also in our semantics that you can't assign anything to that space that's not of the same type. So we know, sort of via an inductive argument, that it will always have the type it has when it starts. I bumped the camera when I laughed at elephants. Yeah, probably. Oh my god. Okay. Well, yeah. That's class. Have a good weekend, everybody. Next week, we'll talk about formalizing our semantics for Sigma, and we'll talk about how one goes about proving type safety for all this shit. Any questions before I log off? Hey Nick, how do you like my new computer? It's Arch and Windows Dual Boot, 1 OS per SSD. It looks pretty slick, I gotta say. Yeah, no, I'm super jelly. Super jelly. Ah, but is it liquid cooled? No, it looks really good. It's kind of funny how like they're making video cards now because they know people who will buy the video card will also buy a computer with a clear case, so that because they like looking at their video card. Ooh, it is liquid cooled. Ooh. AIO. What's AIO? I know very little about liquid cooling. Yeah, also fan cooling is more than enough to do anything. Yeah, yeah. You know, if it's good enough for your house, it's probably good enough for your computer. But... yeah. It's kind of funny. I know a little bit about solar panels, and you'd think that, like, the peak of summer would be when you make the most electricity from solar panels. But you actually, like... once it gets cool in the fall, that you'd be surprised you get a pretty good efficiency boost just from the cooling on a solar panel installation. Radiator fan. Water goes into the CPU, absorbs heat from the copper plate, circulates to the radiator, and fans cool it. Ah, right, gotcha. Okay, well, I gotta log off here. I'll talk to you guys later. Don't do anything I wouldn't do. Also, if anybody's worried about assignment 8 and how to approach it, I put a pretty good hint on pseudo water cooling. I put a pretty good hint on Piazza from like one of the posts yesterday, so go read that if you're having trouble knowing where to start with assignment 8. Take her easy, folks. Don't do anything I wouldn't do.